So, so today we'll be actually talking about the some sort of summary from the last lecture about the excitation stuff, and also we will be covering the frequency encoding and phase encoding and multidimensional imaging vectors. So this is a summary last time. Again, every time when you think about the excitation, you have to think about the Bloch equation and how to solve the Bloch equation. We actually cover how to go from the left frame to rotating frame. And then once you have the rotating frame set up, then you have this B effective term. So you have to calculate or try to understand what is the B effective. Particularly anything that's related to the envelope function is in the transverse component, either X or Y. And anything related to the frequency information, that's over here in the Z direction. So in this situation, we assume the on resonance. So meaning the carrier frequency, which is omega RF, is same as your main magnetic field strength. So it will be canceled out and then 0, and everything else is left over as envelope function. Or if there's a gradient here, then on resonance, it's canceled out. The only component left is the frequency controlled by the gradient. So at different locations, there will be a different frequency component. And by that, you can have a selective excitation. So this is the main difference between the non-selective and selective excitation. The non-selective cases, there's no dependency, or the B effective is not dependent on different location. Whereas the selective excitation, B effective is dependent on different locations. So this is a key component to see the difference between these two. And the way to look at this Bloch equation is you can actually rewrite it as a matrix formula. So in a matrix formula, you also can take a look at the frequency dependency on different locations like omega z or omega of z, and frequency dependent over time, which is controlled by the envelope function of the B1 field. So omega 1 is basically gamma times B1, and B1 of t is basically just the envelope function of the RF. So this is kind of like one slide summary for everything. And by solving this, you can actually understand the dynamics of how the magnetization changes for a given RF pulse and the gradient waveform. And as I said, this is very hard to solve it because it involves multiple first-order differential equations. So we approximate it by just assuming that the tip angle is really, really small, like a small tip, so that the mg is almost equal to m naught, which is the initial condition. And then the theta, the sine theta is equals to theta, cosine theta is equal to 1. Then by just applying this approximation, you can solve this thing, or you can find a solution analytically by having this Fourier transform relationship. So the Fourier transform is basically for a given gradient and B1, you can just shifting the B1 field or the RF waveform to be centered by half duration, and then apply the Fourier transform, and then everything else is your slice profile. And the shape of the profile will be governed by this gradient. So if you're using a different gradient field, then for a given gradient field, slice profile will be a function of spatial position. So after the pulse duration, which is pulse duration of tau, everything is dependent on the location, and that location or the behavior of the magnetization over different location will be expressed as this Fourier transform relationship. Okay? Any questions? I know we covered a lot of math stuff last time, so I know it takes some time to digest it, but if you have any questions, just feel free to let me know.
I think it would be good. I think Kyung did a nice job sort of going through sort of the terms and sort of where things come from, but you can sort of expect that somewhere on your final exam you're going to be asked to kind of work with these expressions and not necessarily these expressions, but sort of just the block expressions in general. And being able to identify what a term means is going to be important. I want you to be able to have some insight that when you look at these things, you can say, oh, okay, that's going to govern this about the magnetization. This is going to govern that about the magnetization.
And in particular, I think Dan and I, we actually try to work hard to make the notation to be consistent. But in some situations, maybe it's not. So it will be great if you just follow through all the kind of derivation, just making sure that whatever you know as a notation is consistent over here. Particularly as we kind of noted, sometimes flip angle, it can be alpha or theta. It depends on how you kind of express it. Those are very, small details, but sometimes it makes people confused. So just making sure that you understand all the notations and follow the same notation, going through all these derivations. Okay? All right. So this is kind of the tool that for a given RF waveform and for a given gradient waveform, you can calculate what's going to be the size profile. The other way to do that, this is an analytical solution, right? You have, boom, you got the solution. The other way is actually, you can directly solve the block equation by numerically. So you can actually solve it, just putting the number and everything, and numerically you can see how things are changing over time, and then you can find the size profile. So those are kind of the two ways to look at the size profile. The numerical solution is actually only one way. So for a given RF pulse, for a given waveform, you can calculate the size profile, but you can actually go backward. Meaning, for a given size profile, sometimes people are interested in designing RF pulse that creates the size profile similar to what the design criteria. For numerical situation, it's not possible, whereas if you have analytical solution, you can do that. So this basically brings up all these potential possibilities to design RF pulses for given specific applications. Like, for example, we want to have a size profile to have a really sharp transition band, but we don't care the rippling artifact. Or we really want to suppress the rippling from the outside band, but then we don't care the transition band, so on and so on. So depending on situation, you can actually design the RF pulse for that specific kind of like desirable features. Or you can also think about, in some situations, the RF pulses has to be follow certain limitation, like pulse duration should be less than 1 millisecond or 2 milliseconds. And for a given limitation, like either hardware limitation or some physiological limitation, for a given limitation, can you make the RF pulse the best? So those kind of questions can be answered once you have the tool available. Okay? So another thing that you have to understand in terms of excitation pulse is the term called time bandwidth product. As defined from the name, it's time multiplied by the bandwidth. Bandwidth is RF bandwidth. So here, it's basically the pulse duration multiplied by the pulse bandwidth. The number doesn't have any unit, but it means a lot in terms of quality of your size profile. And sometimes, how do you calculate the TBW or time bandwidth product? It's actually number of zero crossings in the sync pulses. So just think about it. When you have many zero crossings in the sync pulse, that means sync pulse is really, really long, right? That means if you have a higher number of time bandwidth product, that means you have more ripples included, although it can be long. Then what it means in the size profile is you're going to have a much better shape. So this is kind of the very common number or very practical number. People look at it as a quality of size profile. So for example, if you're using very high time bandwidth product RF pulse, that means your size profile is really good. If you use very low number of time bandwidth product, that means your size profile is really bad. Bad means it's not going to be similar to the rectangular shape. Good means it's going to be very close to the rectangular shape. Okay? So those are kind of simple numbers. Like if the time bandwidth product is 4, let's just say like you're using time bandwidth product is 4, and RF duration is 1, then what is the the RF bandwidth? It's simple, right? I mean, can anyone tell me? It's too simple. 4K, right? 4 kilohertz. What about 16? 16 kilohertz, right? So what that means is actually nothing is kind of free. If you want to have a long or high time band product, but you don't want to have a long RF pulse duration, then something needs to be high. In other words, if you're using the same RF bandwidth, then RF duration is much longer for a given time bandwidth product. Okay? So it's always kind of trade-off, and there's a kind of cost of having high RF bandwidth too. So I'll be actually talking about a little bit of numbers on that side, but always in a practical setup, when you think about the RF pulse, you always have to think about the time bandwidth product. And if the time bandwidth product number, it's a unit less. If the number is high, that means your RF or the size profile quality is good. If the number is low, that means it's not a good size profile. So let's look at a little bit of numbers. Okay. All right. So we're going to take a look at the time bandwidth product. Okay. So the first example will be, let's just assume time bandwidth product is 4. And pulse duration, as I said before, is 1 millisecond. Okay? Then what will be the RF bandwidth? As I said before, the bandwidth should be 4 kilohertz, right? So that if you multiply this and that, that's going to be 4, canceled out each other, correct? Then let's go back to your frequency definition. So the F in your small tip angle approximation definition, F is equal to what? Gamma over 2 pi times GZ times Z. Okay? And gamma over 2 pi is what? This is about 4.257 kilohertz divided by gradient or Gauss. Okay? So let's just assume we want to have 1 centimeter side thickness. Then what will be the required gradient amplitude for a given bandwidth, RF bandwidth? Okay? So if you want to have delta Z to be 1 centimeter, right? Then so I'm just sending everything to here. So the ZZ is equal to gamma over 2 pi Z over F, right? I'm just rewriting this equation, and there's negative sign, but it doesn't really matter. So, and then if you want to have a delta F, which is bandwidth, and you're going to have a delta Z, that's kind of mapping each other. So, for a given time bandwidth product 4, the bandwidth should be 4 kilohertz, right? So that number should be 4 kilohertz. And we want to have delta Z to be 1 centimeter. So this has to be what? 1 centimeter. And we know this constant. This is 4.257. And it's just a calculation for everything, right? So this is 4.257. And always you have to match the units, but it should be okay because this one is what? Kilohertz. kilohertz divided by Gauss and centimeter. So the final unit will be Gauss per centimeter. Okay? So then it's going to be almost, I mean, you can actually calculate using a calculator, but this is 0.9 Gauss per centimeter. So what it says is actually, if you're using a time bandwidth product 4, and the pulse duration is 1 millisecond, that means the bandwidth should be 4 kilohertz, and the required gradient amplitude should be around 1 Gauss per centimeter, or 0.9 Gauss per centimeter. Okay? Let's just look at higher time bandwidth product with the same pulse duration. Okay? So in this situation, you're going to look at time bandwidth product is equal to 16, and the pulse duration is same as 1 millisecond. Okay? Then as I said, the bandwidth has to be 16 kilohertz, right? And then if you want to have 1 centimeter side thickness, then the gradient amplitude required is delta F gamma over 2 pi times delta Z. And this one is what? 16 kilohertz. This is 1 centimeter. And the same thing. Okay? So it's just basically multiplied by 4. Right? So it's almost, but it's not exactly 0.9, so it's actually almost 3.8 Gauss per centimeter. Okay? Okay, the reason that I'm saying here is what? You can set any time bandwidth product, and you can set any pulse duration, but eventually the cost is actually either you have to use high gradient amplitude or low gradient amplitude, depending on duration and the RF bandwidth. So what that means is actually, so for a given 1 millisecond duration, gradient amplitude is required to have almost close to 1 Gauss per centimeter for 1 centimeter side thickness. If you're using time bandwidth product 4. So as I said before, always higher time bandwidth product is good in terms of getting a better size profile. So why not using, higher number always, right? But then think about it. If you use 32 instead of 16, what happens? The required gradient amplitude should be around 8, right? But there's a hardware limit. The hardware cannot accommodate 8 Gauss per centimeter. So there is a strong hardware limit, and then you're not going to achieve that for a given duration. So there is kind of the trade-off always, the RF excitation pulse design is always you have to understand what's going to be your hardware limitation, which is a gradient, as well as B1 amplitude, and what will be your physiological limitation, somewhat related to the pulse duration. So for a given pulse duration that you can allow for a given hardware limitation, like gradient amplitude and a B1 amplitude, you can maximize your time bandwidth product to have a better size profile. Okay? So that's kind of the way that you think about how to design the RF pulse. Just simply looking at the numbers only. We're not talking about the shape or something, just kind of determining the proper time bandwidth product and proper pulse duration can improve a lot of the MR imaging quality because of better size profile for a given restriction. Okay, any questions? Another way to think about it is like this. So we kind of cover we relationship between f and z, right? And this relationship is governed by the slope. Slope will be given by this gradient amplitude, right? I mean, it's gamma over 2 pi gradient amplitude. So having a higher bandwidth means you are having much bigger delta f, right? So if you want to have certain side thickness, so if this is your main side thickness kind of requirement, then you have to have, and if you're having a bigger time, I mean the RF bandwidth, then you have to have a kind of much, kind of steeper slope, meaning higher gradient amplitude. So you can actually think about kind of depending on the gradient amplitude bandwidth, that's going to determine your side thickness. In other words, in a reverse way, for a given side thickness, you have to change either gradient amplitude or the RF bandwidth. RF bandwidth is limited by the B1 amplitude and duration later, and the gradient amplitude is limited by the hardware. So it's always kind of, you can't really have infinite number of RF bandwidth, and or you can't really have infinite amplitude for gradient power. So there is a limitation, and based on those limitations, and for a given design specification, in this case, the slide thickness, you can maximize the quality of your size profile. Okay. Any questions? All right. So that's pretty much about the RF excitation. So on the course website, I actually put the MATLAB scripts for kind of showing how you create the RF pulse and how you test the RF pulse by using a block simulation. Block simulation is basically solving the block equation numerically, or you can actually use the small tip angle approximation by using a Fourier transform relationship. So you can take a look at this script, but as I said, the number one criteria that you have to determine is what? Time bandwidth product. So you have to determine what is the TBW in this situation. I'm just putting 4. And number of samples, it's just it's a digital, everything is kind of array of that, so you have to determine the number of samples. And then I actually provided a so-called window function or window sync function, so you can actually use it if you want to use it. But anyhow, the input is what is going to be your time bandwidth product, which determines how long it is, and then how many samples required to generate. So far, there's no unit included because it's just a number of samples with time bandwidth product, and then you're going to have a shape. And once you have a shape, you may actually kind of assign what is the flip angle value that you want to achieve. So in this case, we just set 90-degree flip angle, and then just changing the kind of flip angle times RF. So this is kind of the way to kind of normalize it. So this is normalized by sum to be 1. So we want to have a sum of all this array to be pi over 2. And then here we are assigning the pulse duration. So pulse duration to be 1 millisecond. That means dt, which is distance between samples, should be pulse duration divided by the sample number. So dt is determined, and then we just make a kind of RF as some appropriate unit as a Gauss. And then this is the bandwidth calculation. So time bandwidth product is pulse duration times bandwidth. So the way to calculate the bandwidth is TBW divided by pulse duration. And Gmax is also determined like that. And here is kind of the plotting portion. So you have RF, and then there is a refocusing pulse, which is half duration of that, and then this is the time information. So this is kind of the simple way to design the RF pulse using a window sync. In this case, we're assuming time bandwidth product is 4, and the pulse duration is 1 millisecond. Okay.
Can I make just a couple comments about that? You're probably, I'm not sure exactly how far you're going to get with this, but I think there's some really nice steps here that he's showing with how you go at the very beginning there, how RF is this window sync function, and then to later where you multiply by the flip angle. Are you going to show them, like what you said that the RF that comes out of WSync, the sum is 1?
Yeah.
Are you going to show them maybe a little picture of kind of why that's the case, or could you just draw one? It's sort of this like small.
There will be the picture of the RF pulse. Yeah, I mean,
there's some nice. My point is, there's some nice scaling steps here that take you from something kind of normalized to an actual B1 pulse at the very end.
Yeah, I see. So the reason that the summation is important is how do we define the flip angle? So at the front of my lecture, the flip angle is defined by what? The integral of the B1 and times gamma, right? So basically, the summation is important because the integration over that B1 field. It's gonna be your flip angle value. So that's why kind of the summation is kind of a big deal later. Okay, so there are 2 different ways to simulate it. Again, one way is using a block simulation. So there's a function. This is I don't know. You covered a little bit on the Brian's tool.
We haven't used Brian's tool yet, but we'll get there.
Yeah. So Brian he's at Stanford. He made a kind of nice numerical simulation tool, so-called block.m. So you can actually use this block simulation, and the input is your B1 gradient and time information, and then you have to determine whether you want to look at the kind of different frequency value or different both resonance or different spatial location. So in this case, we just put the frequency to be 0. So we just want to see the size profile over different location, like here from -2 centimeter to 2 centimeter. And that's it. I guess that's pretty much it. The important thing is actually what's going to be your side thickness. Side thickness is what? This multiplied by Gmax. Gmax is what? This BW divided by gamma 2 pi, which is the calculation that we just did it before. For a given time bandwidth product for 1 millisecond, the Gmax will be around 0.9 Gauss per centimeter. So this will be your Gmax, and then it's included, so your size thickness will be around 1 centimeter. Okay? So after this block simulation, we're going to actually plot as a transverse magnetization. So transverse magnetization should be looking like what? So we're talking about, so let me kind of like, this will be fun, right? So this is after the simulation, and we're going to plot this MXY block, right? So what do we know? We're going to achieve 90-degree flip angle. So there will be a M0, which is along the Z direction. So we're going to achieve 90 degree along how long? Meaning the side thickness will be what? 1 centimeter, right? So from -0.5 to 0.5, everything will be tipped down in an ideal situation. And everything else will be nothing, right? So I'm not sure if you guys understand what I'm talking, but what I want to say is like this. So we're going to plot something like spatial location, and then that there will be -2 centimeter, 2 centimeter. But to achieve 1 centimeter side thickness, this is 0, then 0.5 to 0.5, everything is tipped down. So the length of the MXY will be equal to M0. correct? 90 degree will tipping down everything. So if the M0 is assumed to be 1, that means within this 0.5, everything is 1. Correct? And then outside will be what? Not tipped. So MXY will be what? 0, right? So the ideal situation will be something like that. Okay? So this is kind of our expectation, what we're going to see, because the RF pulse design, we follow all this design criteria, and if you follow all the unit correctly, this is what we're supposed to see. And same thing, we're going to do the same thing using a small tip approximation. In this case, we're using a little bit longer or higher number for the sample size, but everything's the same. We just put the exact same equations in the small tip angle approximation. The final thing is what we just want to kind of apply the Fourier transform. So this is your RF pulse, and take the Fourier transform 1D, and then that's going to be your size profile. So the script is available on the web, so please feel free to download it and just play around it. The core function of it is just called the demo underscore block underscore small. And as I said, it's all in there. So we're going to actually just run it. So the first part is actually, again, as I said, this one is, can you see? Well, so this part is actually basically kind of creating the RF pulse and defining the time bandwidth product, sample size to be 512, and making sure some of the old RF pulse. This is basically integration of B1, right? Is equal to pi over 2, and then the pulse duration is 1, and then just making kind of gamma over gamma, I think it's gamma, or the gamma over 2 pi or gamma, kind of like the constant value to make the right unit of it. And then this is kind of creating all this B1 and the gradient field and the time information, and that's it. So this will be showing what is your RF pulse shape. So as you can see, this is your gradient, this is your RF. During 1 millisecond, it plays the RF pulse. As I said, what's the time bandwidth product again? 4, right? 4 is what? Looking at the zero crossing. How many zero crosses in there? So here's 1, 2, 3, and 4. So 4. So by just looking at it, you can roughly calculate the time bandwidth product. Sometimes people use non-integer time bandwidth product, which is kind of hard to calculate it. But as long as it's an integer value, it's pretty easy to calculate it by just looking at the shape. So what if it's time bandwidth product 2, then what is it? It will be looking like this, right? Because the zero crossing is only 2. If time bandwidth product is 8, then you're going to have something more here. Okay? Any questions? And the gradient, as I said, is close to 1. And later, the half duration of the gradient will take care of the kind of refocusing gradient. Okay. So, if you use block simulation, here's your plot. And you can see it. So, as I said, we're going to actually take a look at here. It's more kind of -4 to 4, but that's okay. The ideal situation is what? As I kind of showed here before, it has to be something 0.5 or 0.5 sharp transition. But because you're using only time bandwidth product 4, this is what you get. So typically, I think this is 0.5 point. So there is some signal coming out of the 0.5, and even kind of less than 0.5 area, it's not perfectly kind of excited, but somewhat close to the rectangular shape. Okay? And if you use a small tip approximation, it's pretty similar, right? So the way that you look at the shape, this versus numerical simulation, it looks pretty similar. So let's do a little bit of fun stuff. So I know we're kind of like out of time, but I don't want to spend too much time on the RF pulse. But RF pulse is actually really fun stuff, so I just want to stimulate more. What if you have higher number, right? Like for example, we cover about 16. So let's consider we have 16 time bandwidth product. Here 16, and then let's see. This is your RF pulse. So let's look at the zero crossing. 1, 2, 3, 4, 5, 6, 7, 8. Right? So the 8, zero crossing. And here's another 8, so 16. High bandwidth product is 16. And duration is, as I said, it's 1. But then, no, actually this is wrong. So I guess it has to be 4. Maybe some calculation was wrong. So the gradient amplitude has to be 4, right? So let's see what happens.
You can still look at this, you can just get a different slice thickness, right?
Yeah, right. Yeah, right. So let's look at that. Okay, so this will be your slice profile. Because you're using the same gradient, that means your slice thickness will be thicker by 4 times. Okay, so that's why this is your slice profile, and it this is kind of like different scales, so hard to compare each other. But definitely this one has much narrow transition band and much closer to the rectangular shape.
So do you guys understand why the slice got thicker? I see some answers kind of. Does someone want to try to explain why the slice got thicker? We kept the time bandwidth product went up by what, factor 4?
Yeah, factor 4. Yeah. Right. So this is maybe
sure.
I will wait until you guys come up with an answer by looking at this. Maybe this will give some of the clue for that. So what do we change? If you increase the time bandwidth product, what do we change? This has increased 4 times, right? But we are using the same gradient. That means what? This has to be increased 4 times, right? Otherwise, this equation doesn't hold at all. So exactly, if you increase the bandwidth 4 times, but you're using the same gradient, your thickness should be increased 4 times. That's exactly the reason for why we're seeing that thicker slice. Okay? Does it make sense? Okay. Anyway, so the code is available. Just feel free to take a look at it. Just play around it. If you have any questions, just ask me anytime.
Was block.c in that folder?
That's a good question. Block.c is there. Have you ever used max function, by the way? So the max function is kind of like the MATLAB is historically very slow, so you have to make it kind of C code version, and then you have to compile it. So .c is there, but then I only compile on a Mac. So if you have a Windows computers, which I don't have, so you have to compile by yourself. It's easy. If you type help max, then it looks at what compiler it's going to use or something. So .c is there, and the compiled version for Mac computers are there, and Linux is there, but no Windows. But there is a way to do that for the Windows computer, so feel free to do that if you're.
You'll use the block function in the course at some point. I think it'll be on homework 3. So the code's there. Give it a shot. If you have a problem, we'll help you solve the problem. It's not that hard, but if you're not familiar with maxing, it's MEX maxing. Then we'll have to walk you through that, or might walk you through.
Okay. All right. So that's about the RF fixation and some of the reviews and examples. Now I'll be actually talking about the frequency encoding and the phase encoding stuff. So first I'll be talking about the 1D imaging, and then kind of expanding to 2D and 3D. And I think, in this situation, I'll be more talking about the Cartesian sampling. And I think later, some of the non-Cartesian imaging may be covered. Not today, though. And then the next one is actually about how do we look at the field of view and a resolution, the relationship between the resolution and the field of view, and the motion artifact. So I kind of like borrowed from the Dan slide. So far we learned kind of like from the magnetization, you record the signal and the voltage information, and then after that you're going to get S of t, which is kind of the signal equation or signal function. And then you have the signal equation. Signal equation is by your mxy and your somewhat kind of like the magnetic field kind of encoding. And then next question is actually how do we form an image, right? Based on this signals. So the way that it works is actually we can control this omega function by using a different gradient, particularly like a gx, gy, gz gradient. And by having this ability to create or manipulate the frequency over different location, we can form an image. So kind of like go back to like three major type of the magnetic field. The main thing is actually B0, B1, and gradient. Using a gradient and a B1, you can actually excite a specific location. That's what we covered before. And after that, using a gradient field, you can create a so-called frequency and phase encoding. And by using the frequency and phase encoding, you can actually form an image. So how do you do it? It's basically kind of combination of excitation and phase and frequency encoding. So excitation will take care of the slice excitation. And then after that, you're kind of applying a different magnetic field at different location by using both phase encoding and a frequency encoding. And then you're recording the signal and then applying the Fourier transform to understand what's the behind image there. Okay? So again, just go back to the MR signal equation. This is kind of the integral over everything. But then assuming you have the excitation, then the integration is only along the transverse component because all this, the spins won't be excited outside the volume of interest or the size of interest. And once you have that, then you only have control in the xy plane or the gradient in xy plane. So the xy gradient will be kind of defined as gamma times gx times z plus gamma times zy plus times z, y. And then once that's done, you plug in everything and then you define as kx to be gamma over 2 pi gx times t, and which is kind of, and ky is gamma over 2 pi gy over t, which is very similar to what we defined previously as small tip approximation. And once you have that, basically you plug in everything over here, and then you define st to be mkxt kyt, and this is basically a Fourier transform of mxy, so you can actually get the images using Fourier transform. I mean, I think you guys kind of like know almost all the background here, right? We're just gonna go back to the basic concept of the imaging components. Just think about it. If you have different proton densities at different locations, like here you have 1, 3, and 2. So the proton density or the strength of your magnetization is different at different locations. And then if you apply this pulse diagram, you're collecting all this signal together, but each one is kind of having a different frequency. So if you have a different frequency and collecting all the signal and apply the 1D Fourier transform, you can decompose all the signal strength. That's all kind of behind, or the theory behind of the MRI. MRI is basically you create the signal and then you assign a different frequency at different location and record the signal and then apply the Fourier transform and decode the strength of that signal. Okay, so as I said, you record the signal, which is kind of like having oscillating at different frequency at different locations with different strength, and then you kind of record all the signal, and then once you apply the Fourier transform, you have 1, 3, 2, which is the strength of that proton density, and you can find that kind of amplitude of that. Okay, I mean, this is a 1D example. In a 2D, what is it? The strength will be your pixel intensity, right? In a 2D domain, higher signal means higher signal, low signal means low intensity. So it becomes more the pixel intensity in the 2D domain if it's a 2D imaging. Okay, so how do we do the 2D imaging? It's basically, again, we have to use a pulse sequence, so-called pulse sequence, and then we're going to actually repeat this pulse sequence by acquiring the data. So here, in a 1D situation, we only need a single signal or single line of the signal. But for 2D situation, you have to get a whole data set within this kx, ky plane. So what that means is actually basically just getting one line of the signal is not going to be enough. You have to get all the necessary information to decode all the 2D information together. So the way that works is actually design this pulse sequence diagram that traverses all this k-space location and getting all the, or recording all the required information, and then applying the Fourier transform to get the imaging information out. So in other words, you can see as signal equation as kind of recording all the necessary k-space information, and this k is controlled by the gradient. Okay, so like you may actually wonder like why many MR physicists are on, and why, you know, in our department in particular we have almost 6 MR faculty members involved. The reason behind is actually there are so many flexibility on designing this ky kz gradient, or the gradient x and gradient y, and also RF pulses too. And once you design everything, there are so many opportunities to reconstruct the images correctly. So there are a lot of areas people can actually look in and improve it, and so on and so on. So, you know, this is one example, but exactly the gradient of x and here it should be y. So x and y, you have lots of flexibility. You can use anything that you wanted, and that creates certain pattern of kx and ky, and that creates the recording pattern. And then as long as you record everything over here and applying the image reconstruction, either a Fourier transform or something else, you can actually get the image back. And the very common way to do that is so-called 2DFT. So just going top to bottom and line by line acquisition. So you go one from left to right, and then going top to bottom, kind of like 1, 1, 1, 1, 1, and then like going through, and you get all the necessary information. And the way it works in the pulse sequence is actually you repeat the same thing, but then changing the gradient in y, which is determining the amplitude of this k, y location, and just repeat it and repeat it. That's how you look at as kind of 2DFT. And that's very, very common way and very practical solution for that. And in many, many situations, this is the number one way to acquire the data. And then once you have that ready, all you need to do is just apply the Fourier transform to recover the image. Okay. Again, this is your k-space data. And k-space data is basically Fourier transform of your image information. And this x is not directly related to k location. So what that means is actually, if I want to know what is the value of m1, 1, which is 1, 1 location of the pixel intensity, you can't really get it because the Fourier transform doesn't allow the 1-to-1 mapping for that. In other words, if you know what is the kx and ky, specific kx, ky location information, you can't really know what's happening in the xy domain. What it gives is actually, it's going to give certain frequency information. For example, at the center, it's a DC component, so if there is no oscillation, this will be your amplitude. And here, this is kind of giving an information on certain kind of spatial frequency information. So for a given spatial frequency information, you have that information. This is nothing related to your spatial location. So sometimes that's a problem because in some situations you only have a very limited information, like half of the k-space data or the fraction of the k-space data, but there's no way you can recover it directly because the Fourier transform in xy domain and k domain is not one-to-one mapping. Any questions? Okay. So next one is actually 3D imaging. So same thing. Instead of applying a thin slice that restricts the volume of your integration, in this situation, you're just either not exciting the specific location or just exciting a very thick slab and then encoding within that slab. So in this case, we're including the z gradient together. So it's going to be gamma zz times x, gamma y times x, gamma gz times z. And here, the kx, ky, kz is included. And the k-space definition is like this. And the pulse sequence will be including this kz component. So if it's non-selective excitation, there will be no gradient here, only the z gradient encoding or phase encoding in the z direction. Or if you're exciting a very thick slab, like 5 centimeter slab or 10 centimeter slab, then you're going to have a very thick kind of slice excitation, and then you're still going to do the phase encoding along the z direction. And everything else is the same thing. So the important thing is you are not getting a continuous signal. You're getting a discrete signal. And that's why a lot of kind of digital signal processing or signal processing is involved, because here everything is related to the sampling. The reason that I'm saying here is actually, so this one is very discrete. Anytime when you specify a specific phase encoding location, that's going to be a specific location. You can't really create a continuous value. Same thing over here. The frequency encoding, the signal you're getting is continuous, but using an A to D converter, you're going to actually get a discrete or digital values later. So the discrete sampling can lead artifact if it's not careful. And for that perspective, you always have to think about what is the field of view and the resolution. Because whenever you have a sampling, and if your field of view is not enough, there will be an aliasing artifact. So the sampling consideration, kind of instead of looking at ST as a continuous value, now we're going to actually take a look at more discrete value. So here we're going to actually assume delta t as a kind of distance of time, and then number of samples here. The same thing over k-space domain, like n times delta t, and that's the index and sampling period. And instead of everything to be continuous, now we're going to actually look at all the dots. So now we're not looking at a continuous line, we're looking at each dot. And once you sample it, you're going to have aliasing artifact that related to your field of view and resolution. Okay, so the discrete sampling in a special frequency domain, and there will be two things that you have to know, which is distance between these samples, either delta ky or delta kx, and how many samples do you have. That's going to be window or w x and wy, or wkx or wky. Right, wkx and wky. So again, the distance is delta ky, and you're going to have how many points you're going to acquire, and how many points acquired times delta kx will be wkx, how many points you're going to acquire in the frequency, the phase encoding direction times ky, delta ky will be wky. So important thing that you have to remember is, again, delta kx, wkx, and delta ky and wky. Because relationship between two will give you the relationship of relationship between the field of view and the resolution. Okay, before going to the details, I'll be simply just covering the simple math in kind of like between the Fourier transform relationship. So whenever you have a convolution, when you apply the Fourier transform, it's going to become multiplication. Okay, that's a simple thing. You have to. I think you're going to encounter in many situations, so you have to memorize it. This is basically convolution becomes multiplication, multiplication becomes convolution. Another thing, when you multiply a constant here, when you apply the Fourier transform, you have to divide it. Okay? It's, I think we covered last time too, when you have a rect times some constant value, in a sinc domain, you have to divide by something. Okay? So this is kind of like, once you stretch it, in the Fourier domain, you have to squeeze it. If you squeeze it, you have to stretch it in the Fourier domain. And shifting, so whenever you have a shifting in one direction in a time domain, then a frequency domain, there will be a phase included. It's a linear phase included. So whenever there is a linear phase, there will be a shifting. There is a shifting and there is a linear phase. Okay? This is very important thing. In particular, in the MR community, this is a lot of this creates a lot of problems because, like, either system imperfection or something. If you have a delay, then it creates a shifting, and it's going to create a shifting in K space, and then it's going to create the linear phase in the image domain. If there's a motion, then it's happening in the shifting in the image domain, and then linear phase in the K space domain. Okay, so a lot of cases like shifting creates a linear phase creates shifting in vice versa domain. So you have to always kind of understand the relationship between two very well. Okay, another thing is it's called Cohn function. Cohn function is kind of a series of delta functions. If you apply the Fourier transform, it's still a Cohn function. So a series of delta function, when you apply the Fourier transform, it's still a Cohn function. We covered it last time. Rect is sinc, and sinc is rect. Always it's exchangeable each other. Okay, so we have a lot of like a huge kind of equation, but the way it works is actually this represents the sampling. So here mkx ky is just a continuous sample or a continuous signal. And then what? You're going to apply the Cohn function, which is the series of delta functions on kx and ky. And this is determined by the distance in kx and distance in ky. And you're gonna apply the rect function that determines what? The width of that sample. So this width is going to be determined by this rect function, and width is actually the wkx and wky. Okay? I mean, it looks really long, so it looks kind of scary, but it's a very simple thing. It's just multiplied by the Cohn function that gives all this infinite samples, and this one will limit how long it's going to have that samples. Okay? So whatever given as a continuous value, if you multiply by this Cohn function, it gives infinite discrete values, and then this will give you a limited discrete value in a 2D domain. And that's going to be governed by what? The delta kx, and the wkx, and delta ky and wky. Okay? Okay, so this is about sampling, kind of getting the discrete samples. but then it's infinite samples, and this is the extent. This kind of limits how many samples you're getting, because you can't really get infinite samples, right? The fact that you're having a lot of samples means it's going to take a lot of time. So you can't really have the infinite samples. So this is going to limit your number of samples. This is going to kind of determine how you go from the continuous to digital or the digitized samples. Okay, and then once you Fourier transform it, the whole reason that we're doing is actually how do we look at the resolution and field of view? Okay, the way to look at it actually, so this is the discrete domain in the samples that we're getting or signals that we're getting. And then once you reconstruct it using a Fourier transform, everything translated using a Fourier transform relationship, right? So multiplication becomes what? Convolution. Confunctions becomes what? Still confunction, right? And this rect function becomes what? Sinc function, right? It's a simple thing. But then there is multiplication, so everything is the convolution. So why this is important? This related to field of view. Because whenever you have a convolution of the confunction, that's going to be replication of that object. So if you have an apple, if you convolute it by the confunction, that means you have multiple apples, correct? If the distance is not long enough or far enough, then the apple will be overlap each other. That means field of view is much smaller, so it's having a folding over artifact. Here, sinc is basically giving a blurring. Giving you a blurring. So meaning if the sinc main of the sinc is actually very wide enough, that means you're convoluting with the sinc function, so your actual signal will be blurred. So the tighter sinc is important, and the sinc governs your resolution. So if the sinc is actually very thick, and then if it's convoluted by some object, then everything will be blurred. If the sinc is actually tight, then everything won't be blurred, correct? So the sinc will be related to your resolution, and the confunction will be related to your field of view. So as I said, this is a field of view related one, and this is a resolution related. Okay? So this is something that mathematically, how do you look at the imaging formation, particularly related to delta kx, wkx, delta ky, and wky. Okay, so let's look at the field of view. So field of view, as I said before, this is basically mxy convoluted by confunction, right? And then the distance of the confunction will be governed by what? Delta kx. So this is exactly what I meant. What it means is actually you have a brain image over here. When you apply the convolution with the confunction, then it's going to be replicated, like infinite number. But I'm just showing just an replication only. And the field of view is the distance between this versus another replication. And that will be governed by 1 over delta kx. Same thing along the y direction, the distance between this and another replication, and that will be governed by 1 over delta ky. So again, delta kx is equal to 1 over field of view, delta ky is 1 over field of view y. Okay? Okay. So let's look at some of the numbers on the field of view in frequency encoding and the phase encoding direction. Okay. So we're going to take a look at the field of view. And first, we'll be looking at the frequency encoding direction. So we're going to look at the frequency encoding. And the frequency encoding will be looking like this. Like you have time, and then like this. And your gradient amplitude will be gx. And there will be some delta t involved, which is a sampling period. Okay? So, as we see before, the delta kx will be determined by what? Just integration over here. Because kx is defined as gamma over 2 pi, and from time 1 to time 2 and the gradient. But in this case, we just want to kind of look at the area of this. So it's going to be 0 to delta t, and then the amplitude will be gx and times dt. So it's going to be just gamma over 2 pi gx times delta t. Right? And the field of view is, as we defined before, field of view x will be 1 over delta kx that means it's going to be 2 pi divided by gamma gx times t. So the question, like you scan some product, some object, and then it looks like the field of view is too small. What should we do? What is an option that you can do? Can you change 2 pi? 2 pi is a constant, right? Gamma is constant. So what can you control? Right. You have two choices. One, changing the gradient amplitude to be higher or lower. Lower means the field of view will go up, right? Or what? Lower the delta t. Delta t is the sampling rate, right? So either you reduce the sampling rate or lower the gradient. Which one is better? I don't know. Does Dan cover the SNR? Okay, so just rule of thumb, SNR is related to how much time you're getting. So it's related to your time of your imaging. Meaning, if you reduce the delta t, is your imaging time is longer or shorter? Shorter. SNR is good or bad? Bad. Okay? So, just rule of thumb, when you see the field of view is a problem, easy solution is, again, using a lower gradient amplitude or lower sampling rate or smaller sampling rate, which is kind of faster sampling rate, right? Then this one is what? It's okay, but you're not really maximizing the gradient amplitude, right? So you're actually kind of underutilizing the hardware capability, but this is okay. If you use this, you're gonna see the SNR goes back. The field of view is bigger, but the SNR is not great. Okay? So the next one is actually a phase encoding correction. So the phase encoding looks like this, right? And every kind of line, you have a different amplitude. And there is a delta zy. This is delta zy. And time is t1. Okay? So we're also going to take a look at delta ky. So delta ky is what? Gamma over 2 pi, right? In this case, the time duration from 0 to ty, so 0 to ty, but then we're only looking at this area, right? So that's going to be delta gy dt. So in other words, is gamma over 2 pi delta gy times t. Okay? So field of view y is equal to what? 1 over delta ky, and it's 2 pi gamma delta y. So the same question, the field of view y doesn't look great. If you want to increase it, how do we do it? So we want to increase the field of view y because there is an aliasing on it, right? How do we do it? Right, so we can reduce the delta gy, right? Then the value goes up. The ty is hard to control because in this case, this is pretty much fixed. You can't really change too much. So this is kind of fixed. All you need to do in many situations is just changing the delta gy. Okay? And yeah. Okay. And last one is something kind of interesting thing that you can see is there's always a 2 pi component here, right? And 2 pi component here. So you can actually rewrite it as 2 pi is equal to field of view y times gamma delta gy times ty, or field of view x gamma gx. Oops. So this is kind of the phase accrual over the field of view, and it has to be exactly 2 pi. So kind of like you can think about across the field of view in y and across the field of view y and x, the phase accrual across the field of view should be equal to 2 pi. Meaning kind of like if you look at all the spins, you assigning different like a frequency information, and if you align everything across the field of view, that should be within the 2 pi period. Otherwise, you're gonna have a field of view problem. I mean, this is not the critical thing to look at it, but this is something that may be useful later for more advanced kind of topics later. But all I want to say is actually, kind of if you look at the spins across all the field of view, and the angle difference between the spins should be within 2 pi. Otherwise, you can't really differentiate those spins well. So, any questions?
Yeah.
Yeah, sure.
What exactly is frequency encoding and phase encoding, and why is the gradients looks that way?
Right, that's a great point. I think hoping the previous lectures actually covered that, but this one is basically kind of like, you can think about it. The kx is defined as 0 to time and gradient, right? So if you look at as a time, so kind of like if you look at the time at this point, let's assume it. So if you think about the time is over here, right? And kx is integration from 0 to time. So there will be a negative value, right? And then if you keep increasing the time, the negative value will be maximum. And then what? It becomes more smaller, and center. And then what? Getting positive, right? So the way it works is actually the kx will be 0, right? And then going negative value, and then coming back, and then going to positive value. That's what it does, based on definition of kx. Correct? phase encoding is basically creating a different amplitude at different repetition. So either you have a smaller positive, smaller negative, but then it keeps changing. What it does is when you combine these two together, then you're basically kind of getting all the signal. So think about it. How do we create this line? It's basically based on this gradient. If you apply this gradient using a kx definition, that means you go from here to negative, and then going positive, 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 and at the end of here, you're ending here. And then if you want to get another line, that means you change your y gradient, which is so-called phase encoding. You change the location, apply the same gx, you go from here to here, and done. The next repetition, you apply the different gy gradient. You go to a different location, going to negative and positive. That's it. Okay? Does it make sense?
Yeah, so if you wanna acquire a line, you don't just go from the left side to the right side. You actually start from the midpoint and it just goes this way.
So starting point has to be always a zero.
Zero.
Here, the starting point has to be 0. So you can go any place, but you have to apply the gradient properly to reach that point. So if you don't have any gy gradient, the only thing that you're going to get is this line. And if you have a positive gy gradient, you go up and getting there. And you have a bigger or higher number, you go there and get it. Higher, go there and get it. And then you keep recording it. And then once you record everything and apply the Fourier transform, you're going to get this.
Can you just explain once which one exactly are meaning TY?
TY? Oh, okay. TY is basically the time on yes. How much time? Yeah. And delta gy is the step size.
My question is, why don't we just use two frequency encoding instead? Why don't we just use two frequency encoding to encode the two dimension, instead of using this phase encoding at the frequency?
Yeah, that's a great question. So historically, right? What's the first MRI paper? The first MRI paper is not based on 2DFT. It's actually based on radial imaging. Radial imaging is also kind of using a two gradient together. The issue is actually the system is not always perfect. Whenever there's an imperfection in the system, one way is more sensitive than the others. And this one tends to be much less sensitive to any kind of system imperfection. And whenever you apply the two gradient together, it gets much more complicated. And the image quality, particularly back then, the system imperfection was really bad, and the image quality was really bad. So that's one aspect. And another thing is actually off resonance. So off resonance is kind of like some imaging acquisition is less sensitive to the off resonance. Some imaging is more sensitive to off resonance. The bottom line is actually whenever you apply the two gradient together, it's going to be much more complicated. But definitely that's still a major research area. A lot of people kind of looking at it. The spiral acquisition is one of the popular methods to maximize the gradient together. EPI is also somewhat similar method. There are a lot of different ways to achieve. So, back to the efficiency, right? Is this efficient? No, because we're not really using or maximizing the gradient amplitude together or gradient information together. So there's definitely a way to improve the efficiency, but then there's also kind of practical issues related to it. So still, it's a kind of open research question. And for certain applications, definitely other acquisition scheme is better than 2DFT. But in most cases, 2DFT tends to be kind of the best. Or maybe the better way to say is actually more robust. Okay. Any other questions? All right, that's field of view. Okay, so to avoid the aliasing effect, meaning to increase the field of view, you have to reduce the delta ky. Then you're going to lose the spatial resolution or increase the scan time. I'll be talking about the y later, but if you reduce the delta ky, what happened? Here we go back to here. If you reduce the delta ky by reducing the delta gy, this governs kind of the resolution. But if you reduce the step size, you need more steps to reach that. Meaning it's going to take longer scan. Or if you fix the number of steps and reducing delta gy, it's going to be reduced. Meaning you're going to lose the resolution. So kind of to get around increasing the field of view, either you can actually lose the resolution or increase the scan time. The field of view, the ky is a little bit different. You have to reduce the delta kx to increase the field of view, but also you can actually utilize the low pass filtering. So along the kx or the x direction, right before the low pass filter, the A to D converter, you can actually apply the low pass filter. That actually restricts certain location to be zeroed out, and you don't have to worry about the field of view aliasing. So this is what I meant. So there is a kind of like going from the voltage information to the S of t, and then you can apply the low pass filtering here. Okay, so what that means is actually, so the field of view y and field of view x is somewhat different. So field of view x, it's easy to control because we have option for using low pass filter. Field of view y is different because if you want to increase the field of view y, what happens? Either you have to lose the resolution or increase the scan time, right? So always, the object is not square. It's sometimes very rectangular depending on shape of the body or location of your object. This is a particular example on the pelvic imaging. So we are actually looking at the pelvic area, and this is very oval shape, right? So one direction is very long, the other direction is not long. And typically, the way it works is actually because the field of view x is much easier to control. So the long axis is typically put it in the x direction, and the short axis in the phasing code. So which direction will be the x direction?
Horizontal.
Yeah, so left, right? Yeah, that's the x direction because we can clearly see that we cut off here, but there is no aliasing on it, right? If the field of view, if this is your phase encoding direction or the y direction, then you have to see some folding over artifact. Because definitely you can see that the object is bigger than the field of view. But because of the low pass filter, you can actually get around it in X. So only benefit of using a low pass filtering is along X, not Y. Because the phase encoding, there is no A to D conversion. It's always kind of discrete points. Whereas the frequency encoding, you're getting as a continuous signal, and then you're converting from analog to digital later. And right before converting to digital side, you can apply the low pass filter. So next one is actually about the spatial resolution. Again, the resolution is related to the convolution of the sinc function. And then main law of the sinc function creates a spatial blurring or related to resolution. So how big is your, or how thick is your sinc function is kind of determining the resolution stuff. So the resolution is defined as 1 over WKX, and resolution Y is defined by 1 over WKY. Okay? So let's look at another example. Okay, in this case, we're going to take a look at the spatial resolution. Okay, and first one, we're going to take a look at, again, frequency encoding. And frequency encoding will be like this. And this is your T GX is your gradient amplitude. We need to calculate what is the WKX, right? So WKX is defined as n read, which is total number of points in the readout direction, times delta kx. And delta kx, we know, we calculated before, so n read times gamma over 2 pi gx times delta t. And then, just think about it, this is what? Delta t times n read is just kind of total time, just total time. Right? So n read is just the number of samples. Delta t is kind of the distance number. So this is basically gamma over 2 pi gx and total read time. Okay. Next one is phase encoding. Again, you have this and this, different values. You have Ty, you have maximum Gy value, and delta G1 time. WKY is equal to number of phase encoding points times delta KY. And delta KY is gamma over 2 pi times delta GY times TY. So I'll just rewrite it. PE times gamma over 2 pi delta GY times TY. So this is what the delta GY times number of points is what? This is basically, this is the step size, and this is the total number. So it's 2 times of maximum value, right? So in other words, you can write it as gamma over 2 pi Ty 2 times GY x. Okay? Two times GY max is basically kind of the length of this, right? And T read is basically the length of that. Any questions? Okay. So that's pretty much about the definition of the resolution and the field of view. The next one that we're going to take a look at is so-called Gibbs ringing. Gibbs ringing is, so as I said, the resolution is somewhat governed by the main lobe of the sync function. But there's also kind of oscillation of the side, all these side lobes. That gives the Gibbs ringing. So if this ringing is too much, then there is a lot of oscillation in the object. And sometimes you can actually clearly see that like this. I don't know if you can see it clearly, but you can see like there's a ripple here. That's so-called Gibbs ring. And even in a diagnostic imaging, sometimes you can see those ripples. Those are not real images. It's called a so-called Gibbs ring. So how do we get rid of the Gibbs ring? Do you know? Okay. Right. Yes. How do we get rid of it? Can you speak up? I don't know.
Make it smoother.
How do you make smoother? I mean, that's right. I think that's correct, but I just want to know more specific approach. Can you speak up? Oh no, this is not the sync that we're designing. This is related to your sample, right? So we can't really touch this. So you can multiply by something, right? I mean, so this is given, right? This is given based on WKX and delta KY, delta KX, WKX, right? I mean, the WKX, WKY, delta KY, delta KX. And then this is given, right? What we can do is actually, we can multiply by windowing function. So in a K-space, sometimes if the Gibbs ring is too much, then we multiply the kind of Hamming window in across the K-space. Then again, it's going to make it smoother. And then it gets rid of the ringing, but then always there's a trade-off, right? What's the trade-off? When you apply the windowing, what happens? Speak up. Losing what? Losing some information is very, I mean, that's right statement, but that's very broad. That's very vague. What information do we lose? I mean, we're talking about the trade-off, so there's got to be something lose, right? Yeah, but what information do we lose? Speak up. I can't really hear. High frequency signal is what? Yeah, so edge information is gone, meaning it has additional blurring. So you're going to lose some resolution, but you're going to actually get rid of the Gibbs ringing. So always MRI, nothing is free. If you do something, you're going to lose something, right? Here, you can get rid of the Gibbs ringing, but then the resolution is not going to be great. So in many cases, yeah, so this is kind of the way that I say. So if you multiply by the windowing function, then kind of like trim down the sync shape, and then you're going to have that. But then the issue is actually, you can take a look at the main lobe. Main lobe is very narrow here, but then the main lobe is much thicker. That means you're going to lose the resolution. So the way that we can take a look at as kind of stated actually, so as I said, you have this M hat KX KY, and then multiply by the windowing function. And then the windowing function will be giving you the behavior or the trade-off, right? And to understand the trade-off, easy way to do that is looking at the point spread function. So this is your acquired K-space data. You can multiply whatever you want, right? So here we are multiplying by some windowing function. That's, purely your decision. But then you need to also understand what's going to be the trade-off, right? To understand the trade-off, easy way to do that is apply the Fourier transform of that windowing function. And it's called point spread function. So point spread function is kind of the way to assess the trade-off of windowing function or whatever the manipulation of the K-space data. Okay. Yeah, so as I said, the main lobe is actually very narrow, and then the point spread function of that windowing function shows that it's very thicker. So it means you're going to have some sort of resolution loss. Okay, so filters can be used to reduce the ringing artifact, but often at the expense of the spatial resolution. But in many cases, the Hamming window seems to be a good balance between the ringing and kind of losing the resolution. So, people look at the balance between two and the trade-off, and then happens to be find Hamming window do a good job in terms of kind of balancing these two. Another one is actually the case-based sampling. So if you kind of assuming that you only acquire 2 lines, and then you get this only, and then apply the Fourier transform, you're not going to get too much information. But if you get more data set, then you have a little bit of kind of more clue, but it's still not a good image quality. And if you get more, it gets better and better. The way that the reason that I'm saying here is actually it's not an equal amount of information. Like meaning, if I show like half of these images, then like half of the images are not showing up or something. Whereas only we're getting a 2 line of that, at least I kind of get an idea on, there's something in, in the middle or something, right? So the information-wise in the image domain, each line does not have or does not contain the equal information. But it takes equal amount of time, because again, each line takes the exact same time, but then the information that contains is different. So this is example of the case-based sampling. So you can see almost at this point, nothing, but then like by the time when it covers the central case-based data, you can see image quality gets much better, right? So again, the time that you're spending for a line is almost the same, but the information that you're getting is very different. So up to here, right, you're spending a lot of time, but nothing's here. But then, boom, by the time it kind of across the DC point and near the central case-based data, you kind of get a lot of information there. So there are, a lot of kind of manipulation, kind of development on efficient sampling. So another way to think about it is kind of getting the central portion first, and then the outer portion later, instead of kind of going from top to bottom. Or you can actually get like some sort of more faster way to acquire the data or something. So there are a lot of research going on how to improve the efficiency. So the next one is actually, I will actually go very quickly on the motion artifact, because I know we cover a lot of stuff and time to go. But this is kind of interesting thing. So the motion artifact is very very interesting and sometimes very hard to understand, because the domain that we are getting is in case-based, or domain that we are recording the signal is in case-based, whereas the domain that we are interested in looking at it is in image domain. So those are kind of not the same domain. So the motion is happening while you're recording the signal, but then the motion artifact happening in the image domain. So it's not going to be easy to kind of understand it. So I will just give some kind of like brief or simple examples on how to understand the motion artifacts. So there are tons of different types of motion artifacts. One could be like respiration, like breathing motion, or some sort of like very like random motion, like you can change your kind of movement or something, or pulsation, kind of very periodic motion, right? And then, as I've said, everything is somewhat different domains. So recording signal is in the case space, but then the artifact happens in the image domain. So it's very important to understand kind of relationship between the case space and the image domain. So the first example is kind of like respiration, or very slow motion, like swallowing or fit motion or something. So in this case, we're just assuming that the object moves from bottom to top very slowly. Then let's see what happens. So while the object is moving, we're recording the signal, right? And at the end of the scanning, the object is already at the top. So in the beginning of the scanning, the object is bottom, but then when the object goes up, the recording is done. So what happened? How do we look at it, right? And then if you apply the Fourier transform of that, you end up having these issues. It's not going to be a average of all three status or something. It's going to be something similar to that. Why is that? The way to look at it is actually the k-space data, because as I said before, although the time of that acquisition is the same, the information that contains per line is different. So particularly you can see the central lines are having a lot of information, whereas the outer k-space portion containing more the frequency or the resolution information. So just think about it, kind of like when the object is at the bottom, you're actually acquiring the top portion of the k-space data, and when you apply the Fourier transform, it's something like that. If you go bottom, the object moves, and then you're going down, and then you have the central information, which has a lot of information, and then going down and down. And then when you sum everything together, then it's going to be like that. So that's kind of the way that you can think of how to understand the motion artifacts when the motion is very slowly moving from top to bottom, I mean the bottom to top. Okay? Another one, so how do we solve the problem? Either taking a breath holding, so not creating any respiratory motion, or you can actually apply the respiratory gating, or sometimes you're just confining the body motion, like training or physical restraint or sedation. Disadvantage is actually sometimes your MR sequence is limited by the breath holding, or you have to increase the scan time or restrict the available TR, or simply patient feels very discomfort. Next one is actually kind of like pulsation. Like whenever you have very fast kind of motion like this, how do we look at it? Again, we're recording signal in k-space, and then you end up having this kind of artifacts. This is very common MR artifacts whenever you try to scan anything that contains a vessel. Vessel has this pulsation, and you're going to see this. So how do we understand it? This is basically, you can separate the static portion and the moving portion out. So static portion is the same thing, but then the moving portion has this sync weighting in k-space, right? And then when you apply the Fourier transform, that's exactly what you're going to see. And static portion is the same thing, so you can just sum it together. Then you're having an MR imaging with it's called ghosting artifacts. So that's what it does. And if you have a kind of much slower pulsation, then the distance becomes narrower. If you have a much faster, then it's going to be much kind of spread it out. So depending on the rate of that pulsation, you're going to see different types of artifacts. But this is a very, very common artifact that you can see. So how do we solve it? Either you can suppress that specific location by applying a spatial pulse sequence, or just swapping the phase encoding and a frequency encoding direction. In many practical situations, just swapping the phase encoding and frequency encoding direction happens a lot because that's easy solution. Because always what's happening is actually this whole line is messed up, but if you just rotate it, sometimes it's okay. Okay. Again, disadvantage is actually either increasing TR or shifting artifact doesn't really help in overall if there are many artifacts included in your image. So sometimes it's not the best solution, but practically swapping the phase encoding and the frequency encoding sometimes solve the problem. Okay. So that's pretty much about it for today. And then last one I just want to say is actually next quarter there will be a kind of follow-up courses, so-called PBM 229. I'll be covering half of that, and the whole Dr. Wu will be covering the rest of the half lectures. It's called Advanced Topics in MRI. Basically, we're going to emphasize a lot of different stuff. Particularly, I'll be more looking at or teaching the RF pulse design. How do we do a fast imaging, the advanced reconstruction, etc., etc. And then Holden will be talking about the fat water imaging sequence. How do we create the better or advanced, or how do you use advanced pulse sequence programming and simulation tools and everything. So if you're interested in that, will be happening next quarter. So just want to let you know the potential course possibility. Okay, so that's pretty much about it. Thank you.
Thanks, Chris.